Okay, so we are continuing with microstrip line, and then after that we will see another popular printed lines which is CPW lines. So with the microstrip line or CPW lines or any other type of printed lines, so the problem we face at millimeter wave frequencies is higher loss. So already we have seen that dielectric loss, conductor loss both increases at millimeter wave frequencies, and not only that, we have one more problem due to surface wave. So if the thickness of the given substrate is thicker compared to the wavelength, then the excitation of surface wave is more. So as the frequency increases, then we should choose a much thinner substrate to avoid the surface wave generation. So before going to other issues for microstrip line, those determines the high frequency limitations of a microstrip line. So let's discuss what are the properties we will be having for a microstrip line resonator. So resonator we used in different applications. So for example, by using resonator we can also design antennas. We know rectangular patch antenna, dipole antenna. So all are examples of different type of resonators. So in these antenna applications, intentionally we want higher radiation loss, but the same resonator we can also use to design filters, typically band pass filter. In those applications, then we don't want any radiation. So if there is any radiation, that will be undesired. Then how to keep radiation minimum for this type of applications? Another important application is the tank circuit, which we use to determine the frequency of an oscillator. So let's first see what are the effects we will be facing at millimeter wave frequencies for a microstrip line resonator. So we are going to consider one microstrip line of length lambda g by 2. So let me draw the top view. So it's showing a microstrip line, its top view. So I'm just drawing the metallic strip part. When its length is lambda g by 2, it will resonate. Now looking at the microstrip line, both ends are open circuited. So we will be having high electric field at this plane and right hand side plane. So from the fringing field, if the electric field and magnetic field they are in same phase, there will be some radiation. And practically what we see, if we keep on increasing the width of this microstrip line resonator, then the part of magnetic field and electric field on these two planes, which is in air and in same phase, increases. So radiation will increase. So what we see then, if I increase the width of this resonator W, then radiation from both of these ends will increase. So if I want to design one antenna, we will choose a higher W, but if I want this resonator for filter applications, in that case the width should be small. But if it's too small, we face one more problem. What is that problem? So in that case, conductor loss will increase. So in practice, what we do for filter applications or for oscillator applications, we use a full wave simulator or electromagnetic solver and then tune the W for minimum loss and for minimum radiation. So this W value, it's an optimum value between the thinnest line and this thicker line. So now let's see, at millimeter wave frequencies we have some other problems. What are those problems? So we have mainly 4 reasons those determines the high frequency operation of a microstrip line. The first one is due to the threshold frequency of coupling to TM0 surface wave mode. Now for a surface wave mode transverse magnetic mode excitation, what we have seen that, let us say this is the microstrip line and the wave propagation direction in z direction, then for TM mode we have two different components of electric field. One component is in the direction of propagation, so Ez component, and another component is perpendicular to the ground plane, which is maximum on the ground plane. Now, if I look at the microstrip field lines, we also have this perpendicular field components. So, the surface wave TM0 mode, it will be easily excited by microstrip line. Now, TM0 mode, it does not have any cutoff frequency. So, we can't avoid this TM0 mode excitation. The excitation of TM0 mode, of course, it depends on substrate thickness. If the thickness increases, in that case we will be having more TM0 mode excitation. So, we can't avoid TM0 mode excitation, but at least we can avoid other higher order modes excitation, like the first one is TM1 mode, which has a cutoff frequency. So, the first limitation, it comes from the cutoff frequency of TM1 modes, which is given by this equation Ft1. Approximately this is equal to c by twice pi d, where c, this is the velocity of light in free space, and d, this is the thickness of the substrate, and epsilon r, this is the dielectric constant of the substrate. So, once we know the substrate parameter, so then we can calculate what would be Ft1 for that given substrate. Next one, this is due to the threshold frequency of coupling to TE1 surface wave mode. So, now if I again go back to microstrip line field configuration, if you remember, for TE mode, TE type surface wave mode, we have only one dominant electric field component, which is parallel to the interface. So, if I look at the microstrip line field configuration, so electric field component of surface wave is parallel. So, that means it is perpendicular to the dominant component of microstrip line. So, what we expect then? Almost no excitation of TE type surface wave mode from microstrip line, because these two field components are orthogonal to each other, and that is why usually for a straight microstrip line there won't be any excitation of TE mode. But now consider bend. So, several times we will be using different type of junctions like T junctions, Y junctions, X junctions, and microstrip line bends whenever we are going to design any components in printed lines. Now, this bend is associated with different type of field components. So, the orientation of these fringing fields, it will change, and they can easily excite TE modes. Now, again for TE0 mode, we do not have any cutoff frequency. So, we can't avoid TE0 mode excitation. So, only thing is that we can keep it minimum by choosing a thinner substrate. So, at least what we can do, we can avoid excitation of TE1 mode. So, in this equation Ft2, this it comes from the cutoff frequency of TE1 mode, and which is given as Ft2 nearly equal to c by 4d square root of epsilon r minus 1. So, for a given substrate, again we can calculate what is the Ft2 for a microstrip line we are expecting in that substrate. Next, threshold frequency of transverse resonance. So, let me first explain what is transverse resonance, then I will come to the threshold frequency. So, before microstrip line, let us recall what is the field configuration for TE10 mode inside a rectangular waveguide. So, if I draw the field strength, it varies sinusoidally and it is maximum on the central plane, and then left and right hand side it decreases. So, this electric field components, it becomes parallel to the side walls of a rectangular waveguide. So obviously then electric field component will be 0 on the side walls, and this length, broadside length of the rectangular waveguide, it should be at least lambda g by 2, otherwise it will not support this TE10 mode excitation. Now consider a microstrip line. So microstrip line strip, let's say it's too wide compared to the wavelength. How wide? Its length, its width is now given as approximately lambda g by 2. So this is the strip, it's sitting over a dielectric, and this is the ground plane of the microstrip line. So I am drawing the cross sectional view. Now if I compare these two figures, for rectangular waveguide we have metallic side walls, so that means we can model it by electric wall, PEC, and for microstrip line it looks like open circuit, so we can model this two surface by PMC. So in this case, this microstrip line, it can support transverse electromagnetic wave, but the field configuration or the variation of electric field along X, it will be different because we have open circuit at two sides. So how is the field configuration now? So if I draw the field strength, so it will be maximum at the two side walls where we have PMC, and it will be minimum on the central plane. So this is called the transverse electromagnetic resonance, or simply we call it transverse resonance. So for this, then the condition is that the width of the strip of a microstrip line, it should be at least lambda g by 2. So it's highly possible when we are dealing with millimeter wave frequencies. Now let's go back to slide. So the threshold frequency of transverse resonance, it's given by FT3, it is approximately C by root epsilon r into twice W plus D, where W, this is the width of the microstrip line. So you see, then it depends on the width of the microstrip line. We have a new parameter which was absent in FT1 or FT2. So if I consider a 50 ohm line, then we have to calculate what is the corresponding width in the given substrate, and D is the thickness of the substrate. So if I increase the thickness of the substrate, obviously for 50 ohm line we have to increase W. If we choose lower epsilon r, in that case also we have to increase W. So that means even if I fix D for smaller epsilon r, FT3 will decrease. And not only that, in when we will be designing millimeter wave components, in that case we don't only deal with 50 ohm line, sometimes we have to use a smaller impedance as small as, let's say, 35.35 ohm, or when we are designing filter, sometimes also we deal with much lower impedance, let's say 20 ohm. So now small impedance, it is associated with large width. So for a practical microwave circuit, then what we do, we have to consider the widest section of the microstrip line and then calculate what is the corresponding FT3. So accordingly you have to choose the substrate for the given frequency of operation. And next, the fourth one, threshold frequency of parallel plate mode. So do you remember that parallel plate excitation? So if we have metal on top and bottom of the substrate, it can also support TEM wave propagation, right? It can also support TE and TM wave propagation. So microstrip line, it's being a strip parallel to ground plane, it can also support similar mode, but TEM mode it's already supporting. So next then we have to consider the cutoff frequencies of TM mode and TE mode. So we are not expecting that microstrip line will be supporting that parallel plate mode excitation due to TE wave and TM waves. So we have one more threshold frequency due to that, which is given as FT4 nearly equal to C by twice T square root of epsilon r, where D is the again thickness of the substrate. So it depends mainly on the thickness of the substrate and the dielectric constant of the substrate. Now for a given substrate, if we calculate all these 4 frequency components, in most of the cases we will see FT3 is minimum. So the minimum among these 4 determines the maximum operating frequency for that given substrate. Not only that, we consider some margin at least 10 to 20%. So please keep it in mind. So next, the variation of epsilon E and Z for a given substrate. What we have seen from the electric field plot in this slide, most of the electromagnetic wave it is confined inside the dielectric, but some of them is also in air. That's why we defined an effective epsilon effective epsilon for this microstrip line, and whose value is smaller than the epsilon r of the substrate and higher than air. Now if the fringing field is less in air, in that case epsilon E will be more close to epsilon r value, right. So if we have less fringing field, that time we can say epsilon E is very close to epsilon r. Now for a given substrate, if I change the operating frequency, then the fringing field component it changes. If I increase frequency, then the thickness of the substrate with respect to lambda g it is increasing. Then we will be having less fringing field in air with increasing frequency. So what do we expect then? Epsilon E it will be more close to epsilon r, or in other words epsilon E it increases with frequency. So we have a plot here, let us see. So this is the calculated epsilon E from this closed form expression. So look at the closed form expression. Epsilon E it's a function of frequency and it's given by epsilon r minus this correction factor. Epsilon E 0 it means the effective epsilon at DC when frequency is tends to 0, and f by f50, where f50 is given here, ft1 is the cutoff frequency defined as this first equation, and W is the width of the strip. Here H is shown instead of D, it represents the thickness of the substrate. Now if we plot epsilon E, it increases with frequency, it's shown by this dashed line. We can correctly determine epsilon E by using any full wave simulator, and we also plotted here that epsilon E by using full wave simulator. So it almost follows this equation, and we see what, that it increases from DC to at 20 gigahertz, at 0 it is approximately 7.5 and it increases to almost 8.5 at 20 gigahertz. So epsilon E it's a function of frequency and it increases with frequency. The problem what we face, characteristics impedance it almost remains constant, but the problem we face with beta it becomes a function of frequency. If we don't consider the accurate value of epsilon E, in that case whatever beta or lambda g we are calculating, so that will be with error, and whatever length we are considering we have to correct it again noting down the actual or accurate values of epsilon E. Next, see the variation of Z naught. So, the Z naught, it is also a function of frequency, but the variation of Z naught with frequency is not that significant like epsilon E. So, in most of the cases we will simply neglect the variation of Z naught. Now, what are the sources of losses for microstrip line? Already we know the reasons. So, the first one is conductor loss, and why? Because with increasing frequency skin depth decreases and the surface resistance will increase. So, conductor loss will increase, and if we choose a thinner substrate, what will happen to suppress the surface wave mode? Thinner substrate, it is associated with higher electric field value. Why? Let us consider again one simple diagram. So, we have two scenario. In first case, this is substrate 1, we are considering again 50 ohm transmission line, and in the second case for substrate 2, but we are considering a thinner substrate here, epsilon r for the first one and second one we are keeping it same. Now, if I send 1 watt of power through the microstrip line 1 and microstrip line 2, and in this case electromagnetic energy is mainly confined below the strip, and here also same thing. Now, since the cross sectional area in the second case is much smaller, what we expect that displacement current or the electric field inside the dielectric, it will be much higher compared to case 1. The induced current Js inside the conductor, that will be also higher compared to case 1. So, in this case then loss will increase, conductor loss will increase. Not only that, since we are considering higher electric field inside the dielectric, in this case dielectric loss also will increase. So, in general the thumb rule is that if I use smaller cross sectional area, loss will increase. So, now let us go back to slide. So, for microstrip line alpha c, it represents the attenuation constant due to conductor loss. This is 8.686 multiplied by this quantity. So, it is a function of frequency. You see here we have two frequency dependent parameters, one f and another delta s, the skin depth, but skin depth it varies inversely with square root of frequency. So, as a result overall alpha c, it increases with square root of f, and not only that, it is a function of characteristics impedance as well as it is a function of width of the microstrip line. As we expected that if we use thinner line, we will be facing higher conductor loss. Now, remember this closed form expression is derived considering a smooth surface, but practically whatever surface we use, that is not smooth. We always having some rough surface. This is one example of rolled copper. So, if you look at the surface, we can't consider it as a smooth surface typically at millimeter wave frequencies, where skin depth is already very small. If you remember, for copper at 100 gigahertz, the skin depth is just 0.21 micrometer, and for this rolled copper, typical surface roughness, it varies between 0.3 to 0.4 micrometer. So, the effect of this surface roughness is that increased alpha c. Let us consider one example. Here we are plotting alpha c in dB per millimeter versus frequency. We are considering the terahertz band just above 300 gigahertz. So, where the skin depth is much smaller compared to that this surface roughness. So, So, let us say the surface roughness capital delta, it is defined as 0.20 micrometer. Then if I consider smooth surface according to this formula, so then the raw loss is roughly 0.5 to 0.6 dB per millimeter over 300 to 400 gigahertz, and it increases to 0.9 to 1.1 dB per millimeter if I consider a surface roughness of 0.20 micrometer. And for this example, we are considering a BCB substrate and a 50 ohm microstrip line. The metal thickness is 3 micrometer and the dielectric thickness is 30 micrometer. So, what should be the optimal thickness of metal whenever we are designing any printed lines? We know the concept of skin depth. So, at 100 gigahertz for copper, we can say that surface that surface density of current, it is already 1 by E times at 0.21 micrometer depth. Now, if I use, let us say, unnecessarily a thicker substrate, let us say a few 100 micrometer, we know that there won't be any current inside. So, in practice, we use a thumb rule that the metal thickness should be at least 5 times of the skin depth, 5 delta S. It is sufficient to design any printed lines. So, for this example, you see, we are considering 300 gigahertz to 400 gigahertz, and we consider 3 micrometer thickness of strip and ground plane. So, that is more than enough for this frequency range. You can compare this value with rectangular waveguide. Alpha c, it is also a function of frequency, but at cutoff it is infinity. But how we define the operating band of a rectangular waveguide? It is 1.25 times fc to 1.9 times of fc, where the loss alpha c, it will be much less compared to microstrip line. How small? Even 10 to 20 times smaller. So, that is why at submillimeter wave frequencies or even at millimeter wave frequencies, we can't use microstrip line for long distance communication. Then what we do? We use these printed lines like microstrip line or CPW line as interconnects for chip to chip connections or from one component to another component connection, which we will be needing to design any millimeter wave circuits. So, let us take a short break, then we will start again. Thank you.